Hey, welcome back to Math with Patrick. Today is February 6th, and we're on to problem 37 from this Daily Epsilon calendar. Okay, when I saw this one for the first time, I immediately was like, what's even going on? There's so much notation here. There's like, one, two, three, four different things, and it's all just math notation. So let's work our way through it and figure out what each part means. Okay. For starters, we have a function called f. It takes the input of t and it places it here and here. So for example, if I wanted to figure out what like f of 2 is, that just means put a 2 wherever you see a t. So 2 on top, 2 on bottom. So it looks like f of 2 is equal to the number 1/3. Okay, so we have a function, we can input numbers in it. I guess the one number we can't input is like -1. Because if I tried plugging in, oh, look, hey, it's Quill. If I tried plugging in a -1 wherever I see a t, so a -1 on top and a -1 on bottom, I'm dividing by 0, and you can't really do that in math. If you ask a calculator this, it would be like error or undefined. So we can't plug in a -1, at least into this function. So the next part I see is that t, which is our input variable, is an element of the real numbers. Or in other words, the real numbers is a big old set of numbers. It's pretty much any number you can think of, from like negative infinity to infinity. And t is going to be any one of those numbers, except for, that's what this minus sign is, except for 0, -1, or 1. So a little bit strange. I mean, that -1 makes sense because earlier I just said that we couldn't plug it in here. But I'm not quite sure why we're getting rid of 0 and 1, but oh well, I guess we can't plug in those values either. Hi, Quilly. Okay. So this next notation is something kind of new. I haven't actually seen this before. So what I'm getting here is some kind of like recursive relationship where the next thing is defined by the one I'm currently at. Okay. Well, this says that n is an element of the natural numbers. And the natural numbers, let's see, I'd say they start at 0, but it doesn't really make sense to, I don't know what the 0th function of t would be. I'm assuming that this function right here is going to be my first function. And then if I take a look at what this says, it says f of, or maybe the second function, f2 of t. This right here is like a 1 plus a 1 is equal to f of f1 of t. And that's what I'm getting from these superscripts, is that this number needs to be 1 more than that one. And it's helping define this recursive relationship where the next thing is defined by using the first, or the previous term, I guess. It looks like I'm just doing successive functioning. Like here I have f of t, essentially. And so I would need to take, here, let's see, f of t. That just says stick the whole function as my input, which is t minus 1 over t plus 1. And then now this notation says stick a t minus 1 over t plus 1 anytime you see a t. So this is, I guess it's called function composition, where you put functions in other functions. What's kind of strange is that we're doing it to itself, and furthermore, we're repeating it over and over again, because it looks like f3 of t is going to be equal to f of f2 of t. Or in other words, to figure out the next function in this repeated function composition, I would need to do f of, and then, I actually found this right here. f2 of t is this whole monstrosity. So I'd have to plug that in as my input. And then to assess what f3 of t is, I would need to take this, subtract 1, and divide by that same input. Oh gosh. And then plus a 1. So, okay, what I'm hoping is that along the way, when we do this successive functioning, there's going to be some simplifications because that is a very, very unwieldy set of fractions. So the last little bit is that we're solving for this x, and it looks like I need to figure out what 9 of these functions compose to each other is, because that's what this 9 here means. I need to do f of, etc. of f of t, and there needs to be 9 of these functions f composed on itself. So I guess what we got to do is just figure out what this function is and then find f3 of t, so on and so forth, until we get up to that 9. All right, that's my plan. So f1 of t, I'm assuming, is just the first function I'm given. And then f2 of t is defined by this recursive relationship. So I just need to do f of 1. So that's going to be f of, and then f of 1 looks like t minus 1 over t plus 1. And then this function notation says to just put my input, this t minus 1 over t plus 1, anytime I see a t. So t minus 1 over t plus 1, and then plus the 1. And I'd like to simplify that. Usually if you see fractions within fractions, a good thing to try to do is find a common denominator. So I could, let's see, on the top part, I could find a common denominator of t plus 1. Because if I have something divided by itself, that's just the same thing as the number 1. And then this t minus 1 stays. And then in the bottom, oh, it looks like my common denominator is going to be another t plus 1. And then this one will be a t plus 1 over t plus 1 as well. And, oh, that's supposed to be a plus because this plus sign is right here. All right. Then now that I have the same denominator, I can subtract my numerators here. Looks like t minus 1 minus t minus 1. These t's will cancel out. And so 1 minus 1 is the same as negative 2. And then in the bottom, I have 2t, and then this minus 1 plus 1 cancels out. So I have a 2t here, okay? And, oh, wow, a lot of simplifications. One thing that I can see is I can just cancel these denominators. If you want to be convinced a little bit more, you could think of fraction division as multiplying by the reciprocal or the flip of the fraction. And then now I can cross off common factors on the top and bottom of fraction multiplication. So those t plus 1s cancel. Oh, and the 2's cancel. So really this whole expression here could be simplified to just, well, there's a negative sign on the top. So I'll call it negative 1 over t. And yeah, that looks to be about it. So wow, f2 of t simplifies down to just negative 1 over t. Well, I need to do this like 7 more times, so let's just keep going because, I'm trying to hit this f9 right here. Okay, f3 of t states that I need to do f of f2 of t, and then f2 of t is just negative 1 over t, so negative 1 over t. And doing what I did before, this just says put a negative 1 over t every time you see that input spot in our original function. So minus 1 on top and a plus 1 on bottom. Same thing, fractions within fractions. Let's try to find a common denominator and simplify. So we have a t over t this time for this number 1, another t over t. And then, so I have a negative 1 minus t over t in the top. And I get a, let's see, negative 1 plus t all over t in the denominator. And I'll do this step quickly this time. These t's cancel out, and so I'm left with negative 1 minus t over negative 1 plus t. And well, there's a lot of negative signs here. I think if I negate everything, I'm not changing its value, right? Because if I negate the top and bottom of some fraction, it stays the same. And then that way I'll just have fewer negative signs to worry about. So let's see, I'll negate the top, And then negating the bottom, I have t minus 1 right now. So I'll have 1 minus t like this. And that feels a little bit neater. So, okay, f3 of t is, well, let me see if I can match it to the first one. Maybe just to keep the notation kind of similar, I'll do t plus 1 and then negative t, oh gosh, what was it? Plus 1. And then f4 of t, actually, I have a, I have a hunch. I think that this is just going to be t. My guess here is that I could probably compose f2 of t. That's going to be, let's see, negative 1 over t. I'm composing this with itself. Then fraction division says I should just flip that. So negative 1 times negative t over 1. And then, yeah, that's just t. So I think this is just t. I'll just do it the right way and do the function composition as it's defined recursively. Because this definition here doesn't say that I can skip back 2 spots. It just says I can skip back 1. So I still should do f of, and then f3 of t, which is right here. T plus 1 over negative t plus 1. And then so back to fractions and fractions. Okay. T plus 1 over negative t plus 1 minus 1 on the top. Then t plus 1 over negative t plus 1 minus 1 on the bottom. Find a common denominator. So it's negative t plus 1 for both of these. Then this becomes a negative t plus 1 over negative t plus 1. So t plus 1 minus negative t plus 1 on the top. And then t, that's a plus right here, right? Yeah. T plus 1 minus a negative t plus 1 on the bottom. Nope. That's supposed to be a plus sign right here. Glad I caught that one. Okay. T minus negative t is 2t. 1 minus 1 is 0. So I've dealt with this. And then, yeah, these ones cancel here. And then in the denominator, I have t plus negative t. That cancels. And so 1 plus 1 is 2. There we go. So just like I thought, all of this stuff just simplifies down to a t. And this is actually so nice. I mean, the process to get here wasn't, to be honest. But the fact that f4 of t is just t means that this is like the identity function. So when I try doing, yeah, f5 of t is going to be, I just had to convince myself there, is going to be f of f4 of t. And then we just established that f4 of t is just t. So the fifth one is going to be the same as what I started with, this one right here, and I'm just going to go in a whole cycle. So that's good. I don't need to actually keep going with this process because it loops over itself. And now we're getting closer to actually getting a number, and hopefully it'll be 6 in the end. So therefore, f9 of t, I can backtrack 4 steps and get f5 of t, and backtrack another 4 steps and get f1 of t, which is just a function at the start. That was t minus 1 over t plus 1. f8 of t is going to be the same as f4 of t, and I can see that here that's just t. And then f2 of t is this one right here, so negative 1 over t. f2 of t is equal to negative 1 over t. So now I can just plug in these numbers. I have a half, a 9, and a 10. So let's see, f2 of a half, and then plus f9 of 9 times f8 of 10. Right? Just double checking. Yep. Okay. This function notation says look here and plug in a 1/2. So that's negative 1 over 1/2. 1/2 goes into 1 2 times, make it negative. So that's a negative 2. Plus f9 of 9 is going to be here. So I'll go 9 minus 1 over 9 plus 1, which is the same as 8 tenths. I guess I could reduce it. And then f8 of 10, oh yeah, f of 8 and f of 4 are just like an identity function, return the input. So f8 of 10 is just 10. Okay, I'm glad I didn't reduce it actually, because these 10s cancel out. 8 tenths times 10 is 8. And then, yeah, -2 plus 8 is finally 6. And that's today's date, and we're all done. All right, thanks for coming along. Hope this helped. I'll see you in the next one. All right, bye-bye. Oh, wait, before you go, two things. Thing one, I just realized that it's really important that we had this domain restriction here. Earlier, I was saying like it makes sense that I can't plug in a -1 because it didn't work for F1. But then the 0 and the 1 kind of confused me for a bit. But if you look here, we can't plug in a 0 or else it's undefined. And then here, we can't plug in a 1 or else it's undefined. So this cyclical nature of this function composition only works when we don't plug in a -1, 0, or 1. And then thing number two, I know of another math concept that has a cyclical nature of 4, and that's successive powers of I. So I'm not quite sure how to make this connection, but if we had something like I and then like I squared, I cubed, I to the fourth, that's also something that has this repetitive nature. And so maybe there's something kind of like something going on here with complex numbers where like this feels a lot like the number 1 because it's like the identity function. This feels a lot like the -1 because it's like both a reciprocal and a negation. And then maybe these ones correspond to I and -I. Now, I don't really have a way to prove it, but because it has a cyclical nature, because it has a period of 4, there's something going on here that feels very, very similar to complex numbers. I can't quite put my finger on it. So if you have some ideas, please let me know. I'd love to hear them. But yeah, I just wanted to share those two things before we actually sign off today. Okay, I'm all done. Now I'll see you in the next one. Bye-bye.